Okay, Organic Chemistry 2, Chemistry 3111. This is Chapter 18. It deals with aromatic substitution reactions. And the first type of substitution reaction we're going to cover in this chapter is called an electrophilic aromatic substitution reaction. It's exactly what it sounds like. First of all, you're doing a substitution reaction on an aromatic ring, and you're doing it by putting the aromatic ring in the presence of a strong electrophile. So we're going to talk all about that. And we've seen in chapter 17 how aromatic pi bonds are less reactive than typical alkenes. Just to remind you, if you take cyclohexene and treat it with bromine, we get anti-addition across that double bond, and we get trans 1,2-dibromo cyclohexane. But if we try the same thing with benzene, again in chapter 17, we said, well, benzene has a closed shell electron configuration. All of the bonding molecular orbitals are filled, and therefore it is unreactive. It has a stability associated with it such that it won't react with bromine. This won't happen. And so is there anything that we can do to cause benzene to become reactive towards an electrophile? Well, let's take a look here. If we take benzene and we subject it to bromine, but we put some iron in the reaction mixture, just some iron filings, we see that we do get a substitution reaction occurring, and it occurs in a high yield. 75%, that's not bad. Now, again, we see that this is a substitution reaction. Why? Because we're substituting a hydrogen for a bromine. And what we're doing is we're making a very electrophilic source of bromine. I'm going to talk about that more in a second. And we say it's an electrophilic aromatic substitution because we're substituting on an aromatic ring. Now, again, what's the point of adding the iron here? The point of adding the iron is that we end up making iron 3 bromide, which can react as a Lewis acid with bromine to make it a very electrophilic source of bromine that I'm going to talk about in a second. But before we get into that, electrophilic aromatic substitution, which we sometimes refer to as EAS reactions, is where an aromatic proton is replaced by an electrophile. And the ring acts as a nucleophile. So what we're doing in every single one of these reactions is we're replacing a hydrogen. It could be with a bromine to make an aryl bromide rather. It could be with chlorine to make an aryl chloride. It could be making a nitro group, so that's called nitration. The first two we would refer to as halogenation. This one we would refer to as nitration. We'll discuss that. This is called a sulfonic acid. And so this would be called sulfonation. I'll just scribble it in here, sulfonation. These are just words you'll hear me say. The next one is an alkylation, and I think you all know what an alkyl group is by now. So alkylation. And this one is called acylation, because this is an acyl group. And of course, this is an alkyl group. So just some terminology that I'm going to use from time to time. But the bottom line is that we're reacting our aromatic ring with a strong electrophile, and the ring is actually going to use electrons and act as a nucleophile, like this. Something that we haven't seen before, something brand new. Well, I guess it's because we haven't seen an electrophile that's powerful enough. If we go back to that bromination reaction, so this is going all the way back to chapter 8, and just talking about the mechanism of the reaction between cyclohexene, which is a nucleophile, and Br2, which is our nucleophile. And I don't know what's going on here, but this is supposed to be delta plus and delta minus. And we know that that can happen because even though bromine, Br2, is not a polar molecule, we know that it's polarizable. And so it has, it can have an induced dipole like this, or a temporary dipole. And so our double bond in our cyclohexene is going to act as like a nucleophile. And then we're going to break this bond here, and then we make the bromonium ion. And I don't have time to go over the entire thing, but this is just a little review of Organic Chemistry 1. You make a bromonium ion like this. And then, of course, the bromide comes in as a nucleophile. Anyhow, I can't help myself here. There you go. So bromide comes in there like this. But this electrophile, just Br2, is not strong enough to react with an aromatic ring. Won't react with an aromatic ring. And so a Lewis acid catalyst is needed to make bromine electrophilic enough to be attacked by the pi electrons in an aromatic ring. You've got to wave something in front of the aromatic ring to say, like, look how reactive this is, you aromatic ring, you now react, okay? So what happens? We mix some iron with some bromine, and we end up making iron 3 bromide. And iron 3 bromide, if you draw the Lewis structure of iron 3 bromide, it just, it's nothing really special. But what's important to recognize is that this is a Lewis acid. What's a Lewis acid? Is it an electron acceptor or an electron donor? It is an electron acceptor. And who can it accept electrons from? It can accept electrons from Br2. So here's our Lewis acid, our FeBr3, and it's reacting with bromine, which is essentially acting as a Lewis base, an electron donor. And then we end up making this intermediate. And you can see that this, I would call this a complex. This complex, it says it's in equilibrium with this FeBr4 anion in an electrophilic bromine. So we have bromine surrounded by 6 valence electrons. And so you have a bromine cation. Wow, now that's a very potent electrophile. That thing is ready to react. And if an aromatic ring sees that thing, it's going to be like, hello. It's going to react like nobody's business. Okay, so you have to put some kind of electrophile that's very powerful into the presence of the aromatic ring. Now I'll just level with you. Our book never draws the mechanism like this, okay? Because it never draws the electrophile like this. Our book always draws the electrophile like this. It always does it that way. And the way that it draws the arrow of the ring attacking the bromine, it will always do it like this. It'll go like that. So it'll show the pi bond in the aromatic ring breaking, attacking the bromine on the end, and then you end up with the bromine attached to the aromatic ring with a positive charge. And if you want to see that in full detail, well, I've got some good news. I've got it for you right here. So here's our mechanism of electrophilic aromatic substitution. So here's our complex, okay, between the Lewis acid and the Lewis base. So our aromatic ring acts as a nucleophile. This is, again, is something we've seen many nucleophilic attacks, but we've never seen an aromatic ring act like a nucleophile. Well, today's a new day, so something new. But when you break that pi bond, you form one bond to the bromine. That's this one here. But now this carbon only has 3 bonds, and it doesn't have the double bond. So now you have a carbocation, and that is an allylic carbocation. You can see here, and we can draw 3 resonance structures, and we call this a sigma complex. Sometimes you'll see that called an arenium ion. So arenium ion. If you're perusing the internet, you might see that from time to time. But we end up with this resonance stabilized sigma complex. And then in the last step, we have our FeBr4 minus anion, or FeBr4 minus, which removes the proton on this carbon where the substitution occurred to regenerate the aromatic ring. And then we're left over with HBr and our Lewis acid catalyst regenerated. So our Lewis acid catalyst gets regenerated in the end, and that's why we call it a Lewis acid catalyst, because remember, a catalyst gets recycled over and over. The bottom line of this page is step 1 is nucleophilic attack by the aromatic ring, and you make a sigma complex. And then in step 2, it's just a deprotonation. So it's literally a 2-step mechanism with, some resonance structures that you need to be aware of somewhere in the middle. And I have some good news. This isn't the last time you're going to see this, this mechanism. Well, if we just think about the free energy of the process that's occurring here, we're starting out with benzene, starting out with our aromatic ring here, and then we look at the activation energy to make the substitution product versus the addition product. Well, you can see that it's an uphill climb going through the sigma complex and making the addition product. Here our delta G would be positive, And so that would be a non-spontaneous process, whereas if we do the substitution, our delta G is negative, and so this is going to be a spontaneous process. And that explains why substitution is observed. It's exergonic, it's spontaneous, the delta G is negative, however you want to frame it. And addition would be an endergonic process. It would be a disfavored process. Somebody asked me, do you need to know the mechanism? Yes. Okay, yes. You must know this mechanism. This is one of the most important mechanisms in organic chemistry, is an electrophilic aromatic substitution mechanism. Extremely important. Only 2 steps. Well, are there other options besides using iron and making iron 3 bromide? And the answer is yeah. There are other Lewis acids you could use to add a bromine to an aromatic ring. Instead of using FeBr3, iron 3 bromide, you could just use aluminum tribromide. That will work as well. So AlBr3, which is also another Lewis. It's also a Lewis acid. It says, look, the mechanism would be the exact same as when FeBr3 is used. Now, if you're asking me, well, when would I use FeBr3 and when would I use AlBr3? Here's my answer, and this is the truth. If you were doing this on some kind of molecule that had never been invented before, that nobody's ever made in human history, you would try both. That's all you would do. You would try both, and you'd say, well, one of them gives me a 90% yield, and one of them gives me a 65% yield. I'll stick with the one that gives me the 90% yield. So it's probably substrate specific. It depends on a case-by-case scenario. Next, instead of adding a bromine, I said that you could also do chlorination. It says here that benzene can undergo chlorination by using chlorine instead of bromine, and so you would use a Lewis acid like aluminum chloride or aluminum trichloride, and chlorine benzene or the aryl chloride here. Now, if you're wondering, why didn't you bring up fluorination and iodination? That's a great question. And fluorination is too violent. Are there ways to put fluorines on aromatic rings? Sure, there are some things, and we'll actually see a little bit of those later on. We'll talk about something called the CHEM reaction, but that's for another day. So don't worry about that today. But generally speaking, just plain old fluorination is pretty much too violent to be practical, and iodination is generally speaking slow. However, there is an exception to that, and I'm going to write this down here. It's very rare that I will refer to a specific question in the book, but I want everybody to take a look at question 18.1 in the book. It's the first question. So I want everybody to do that question when you're doing your practice, and it discusses iodination. It says that you can do iodination if you take benzene and you treat it with iodine and copper 2 chloride. So copper 2 chloride is the Lewis acid. That will give you iodobenzene. So again, that's very rare for me to tell you to look at a question and cover something like that, but I want you to take a look at this question specifically before you step into the quiz. So there is a way to add iodine. It can be done, and it is covered in the very first question in the textbook. So look, let's take another peek at that mechanism. Right, Sandrina? What's the best way to memorize the mechanism? Repeat it over and over. And you notice that the electrophilic aromatic substitution mechanism for chlorination is analogous, which is just a fancy word for the same thing as it was for bromination. We have the nucleophilic attack in the first step. So we have our aromatic ring acting as a nucleophile. Now, I like to always start the curved arrow on the carbon, and kind of drag it through like that. So I say, well, this is where my new bond is going to be. You form the sigma complex. You should be able to draw all 3 of these resonance structures. And then the very last step involves a proton transfer where we regenerate the aromatic ring. It says here you restore the aromaticity, and they left out the other products that you would get. So from this, you would also get your aluminum trichloride. So you'd regenerate your catalyst, and you'd also end up with some HCl, right? Because here you're forming a bond between H and Cl to make some hydrochloric acid. Just like that. So halogenation, same thing. Step one, nucleophilic attack. Then you go to the sigma complex, and then you do, in the second step, a proton transfer, and you install your electrophilic aromatic substitution. And again, just to remind you, if you're the kind of person who likes to look everything up on the internet, like, oh, I need more information, I want more background on this. Some people call the sigma complex the rhenium ion. If you are, finding free textbooks on the internet or something like that, you might find that. So if we skip all the way to the end of the slides, all the way to the very end, what have we covered so far? We've covered bromination, we've covered chlorination, and I also told you that you can do iodination with iodine and copper 2 chloride to install an iodine. And this is covered in question 18.1 that I want you to look at. So next, we're going to cover nitration and sulfonation as well. I don't think they're in that particular order, but we're going to cover those next. So let's go all the way back to the top. It's a long way to the top, right? Anyhow, so where were we? Somewhere around here, sulfonation. So let's start off with sulfonation. Go ahead.
Ask a question. Do you have to use AlCl3 for the chlorination, or could you also use AlBr3 interchangeably?
For bromination, you can use aluminum bromide, and you can use an iron 3 bromide. And the same thing for the chlorination. You could use aluminum chloride or iron 3 chloride. Either one would work.
Okay, but you can't use aluminum bromide for chlorination.
No, definitely not.
Okay.
Okay, you can't mix the halogen with a Lewis acid that has a different halogen on it. Okay. The Lewis acid and the halogen that you're using have to be compatible. They have to be identical. Yep. All right.
Thank you.
Does that answer it?
Yes, thank you.
Okay, good enough. All right. Cool. Well, let's move on to sulfonation. Sulfonation sounds like a nation of sulfurs or something. Anyhow, sulfonation occurs by using SO3. So SO3, a little bit of practice of your covalent compound nomenclature. So this would be sulfur trioxide. So using sulfur trioxide as an electrophile and sulfuric acid as the acid catalyst. Now, sulfur trioxide is a gas. And so what we use is fuming sulfuric acid. And fuming sulfuric acid is just a mixture of sulfuric acid and sulfur trioxide. So they basically take aqueous sulfuric acid and they bubble sulfur trioxide through it. So inside the fuming sulfuric acid, you have the SO3 gas in there already. And you can imagine that sulfur trioxide is a pretty dandy electrophile, as it says here. It says that it's the electrophile. Now, why would that be such a great electrophile? Well, here's the electrostatic potential map, the EPM of sulfur trioxide. Now, if you're still on the fence about what these diagrams mean, all it means is that you can just look at the colors and kind of see where the electron density is. And where the electrostatic potential map is more red, that means it's more negative. So delta minus, delta minus, delta minus. And where, delta minus. And where it's blue, then it's kind of positive. It's more positive. So we see that this sulfur is really electrophilic. There's very little electron density there. That means that an aromatic ring, if you put this in the presence of a benzene ring, the benzene is just like, hello, oops, that's not a very good curved arrow. Maybe like this, okay, something like that. It wants to attack that really badly. Now, why would it be that sulfur would be so electropositive? I can give you two reasons. Number one is that oxygen is more electronegative than sulfur. There's no arguing that. Oxygen has an electronegativity of 3.5. So we'll put 3.5 for oxygen. And sulfur is close to 2.5. It's something like that. It's close to 2.5, 2.6 maybe. Anyhow, so there's a pretty big difference in terms of electronegativity, but there's another reason. You remember what a pi bond is? A pi bond results from the overlap, the side-to-side overlap of two p orbitals. Well, if you look at the periodic table, where do you find oxygen? Oxygen is in period 2, where sulfur is in the third period. So if you look at the overlap between the 3p orbital, this is a 3p orbital, and the 2p orbital of the sulfur and the oxygen respectively, the overlap is really crappy. And the reason why it's inefficient is because there's so much difference in size. If you think about a carbonyl, for example, if you have a carbon oxygen and you have a pi bond on it, well, both of the 2p orbitals come from the same period, you know, they're both 2p's, and so the orbital overlap is much more efficient in a carbonyl. But again, when we have a sulfur oxygen double bond, we see this many times in organic chemistry, only a few times in this class, but if you study advanced organic chemistry, what you really conclude as an organic chemist is that the sulfur oxygen double bond has a lot of single bond character to it, which imparts some really interesting reactivity to that. Anyhow, we don't go into much more detail on it than that, but the bottom line, after all of that, me rambling for the last like 4 minutes, is nothing more than sulfur trioxide is a great electrophile. So if you put an aromatic ring in the presence of sulfur trioxide, what's going to happen? It's going to attack it. So we attack it, and after our nucleophilic attack, what do we get? We get our sigma complex. You need to be able to draw all 3 of those resonance contributors. And remember that when you have sulfuric acid, when we're talking about sulfuric acid is made in water. That's why we call it sulfuric acid. When you see the aqueous, it means it's acid. So it's in water. What's going to be the base that can come along and rip a proton off? It's going to be a water molecule that can come and rip that proton off and regenerate hydronium. Because remember, going back to acids and bases in general chemistry 2 and organic chemistry 1, if you have a mixture of sulfuric acid and water, what's the major acid that's present? It's going to be hydronium. So we rip a proton off of our sigma complex to restore the aromaticity, and then we protonate this, you'd call that a sulfonate, to make a sulfonic acid. So sulfonic acid, just like that. Here you go. Same mechanism that we saw before. Step 1, nucleophilic attack. Step 2, proton transfer. It is a little bit different. I fully admit that. It's not the same electrophile, but we end up making a sulfonic acid. Now, if you're wondering, maybe you're not, but if you are wondering, what's the point of a sulfonic acid, Mr. Dion? Well, there's lots of things you can do with sulfonic acids. Now, I'll be totally frank with you. We don't look at a ton of things that you can do with sulfonic acids. However, this is a very important reaction because we do use the sulfonic acid as what we call a blocking group. And I'm going to explain, it's not a protecting group, a blocking group. So it blocks certain sites from substitution. And I'm going to go over that with you in detail. So what that brings me to is the next slide, where you need to understand that if you take your aromatic ring, so you take your benzene molecule, and you treat it with fuming sulfuric acid, you make the sulfonic acid. So we get a sulfonic acid, which I told you can be used as a blocking group. And again, we're going to look at that later in the chapter. So that's not for right this moment. So don't stress about it right now. However, if you treat it with dilute sulfuric acid, it just rips it off. And the mechanism for the removal of the sulfonic acid is the same as the formation. It's just the exact reverse mechanism, nothing more than that, which is based off of the principle of microscopic reversibility. But anyhow, the bottom line is you can install the sulfonic acid with fuming concentrated sulfuric acid, and you can remove it with dilute sulfuric acid. And again, right now you might be wondering, why are you teaching me this? Why do I have to know this? Well, again, It's going to come up later on in the chapter, and it will be of great synthetic utility to us later on. Okay, so now we've covered halogenation, chlorination, bromination. I told you about question 18.1 that covers iodination, and we've covered sulfonation. Let's cover one more type of electrophilic aromatic substitution, at least nitration, and then maybe we'll take a short break before we get into Friedel-Crafts, alkylation and acylation, which is kind of long. So just to give you an idea, we don't get to practice really any problems until we cover the first 6 sections of the chapter. But the good news is you're through more than half of it now, kind of half of the intro before we take a look at some practice problems. You got to learn the first few types of substitution, then we get to try some problems. Okay, 18.4, nitration. So again, halogenation, we got that down. Sulfonation, got that down. Now we're going to talk about nitration, installing a nitro group. You should know how to draw the Lewis structure of a nitro. This is, something that all students need to be able to draw. That a nitro actually looks like this. You have a nitrogen. It's got a double bond and 2 single bonds. Therefore, it has a positive charge. And then you have a negative charge on one of the oxygens. That is a nitro group. Very important. And let's see here. It says nitration. How do you do it? You mix nitric acid as the source of the electrophile with sulfuric acid as the acid catalyst. And the way that this reaction works is that what scientists think is that you make something called a nitronium ion. Now, if you take Chemistry 3112 with Mr. Geiger or me in the spring or the fall semester, we usually do a nitration reaction. Not this exact reaction, but we do something very similar to it so that we make the nitronium ion. And that nitronium ion has a really neat Lewis structure. It looks like this. So this is the nitronium ion. So we've got a positive charge on a nitrogen. And you can imagine that if you have this nitronium ion produced in situ, so that just means in the reaction mixture, that this is such a powerful electrophile that double bond's just going to, or sorry, the aromatic ring is going to attack that like nothing. Anyhow, and we'll get into the mechanism in a second. That's coming up in a second. But you might be wondering, well, I'm mixing 2 acids. Mixing 2 acids, how does that work exactly? Because in order to make the nitronium, you actually have to protonate nitric acid. Now, if you're going, what? How would I protonate nitric acid? Isn't nitric acid one of the strong acids that you made me memorize? How would you protonate it? Well, remember that the pKa of sulfuric acid is -9, and the pK of nitric acid is around -2. I think in the book it says -1.4, so I might be off by a little bit. So the difference is 7.6. So that means that sulfuric acid is more than 10 million times more acidic than nitric acid. So remember, acidity is relative. And thus, sulfuric acid can protonate nitric acid no problem, and it loses a leaving group, in this step here, and we end up making a nitronium ion. And this is our active electrophile in nitration. And again, the nitronium ion, as you can see, is highly electrophilic. It's got a positive charge plunked right there on the nitrogen. So what's our mechanism going to look like? Well, let's take a peek at the mechanism for nitration. I bet you that it will involve a nucleophilic attack, a sigma complex, and a proton transfer. What do you think? Let's roll the dice here. Well, what do you know? It involves a nucleophilic attack on the nitronium. Same old first step. We make our sigma complex. You should know how to draw all those resonance structures. And then water is going to come in, right? Because we're in sulfuric acid and nitric acid, which are acids dissolved in water. So water would behave as a base. Come, rip a proton off, and we restore the aromatic ring, and that's it. Right? And you end up regenerating the acid catalyst along the way. You'd also end up with H3O plus. And so now you've made nitrobenzene. That's what you'd call this compound. This would be nitrobenzene. A little bit of aromatic nomenclature for you there. Now, if you're wondering, okay, I've learned how to install a nitro group, but if you go look at marketed drugs, if you just look at some marketed drugs, and maybe we should do that some days, go and look at some new functional groups, especially now that you know so much about aromatic rings. You won't find a whole lot of marketed drugs that have nitro groups in them. There are some, yes, I'm fully aware of that, but not many. And so what could you do with a nitro group? Well, there's some cool stuff that you can do with a nitro group. And I worked in a HIV program, so you all know what HIV is, I presume. So anyhow, I worked in an HIV program for years, and a reaction that we did in that program all the time was this reaction here. We would make nitros, we would install nitro groups on aromatic rings, but then we would convert them to amines. And if you look at our schedule in Organic Chemistry 2, Chapter 22, my blue pen, Chapter 22 deals with nothing but amines. And so if you can find a way to make an amine, you can do all kinds of interesting chemistry with amines. And so let's discuss this. How do you make an amine from a nitro? Well, it's a two-step process. The mechanism is not covered in our textbook whatsoever. It's a mechanism that you might find some details about it if you peruse the internet, but my guess is it's one of those things that's probably not completely understood. But here you go. Very inexpensive chemistry. All you do is you take your nitro group on your aromatic ring and you combine it with HCl and iron or zinc. And I literally mean you put some zinc metal as just filings in there, or iron filings, just a little bit of one of those metals as a powder. You stir it around, you filter off the metal. But since you're in acid, you can't have an amine in acid. What that would give you is the conjugate acid of the amine. So you'd actually end up with this compound. So you'd end up with the aniline ion, NH3 plus. And so this is after the first step. So then after the second step, you just treat it with sodium hydroxide and that rips the proton off. And you restore and you make, in this case, you end up with aniline, which is a great compound and it's lots of synthetic utility. And so you can see how you can combine all these reactions to install an amino group on a benzene ring. First step is going to be nitration, followed by the reduction. So remember reduction, and I don't think I even used that word, but reduction in organic chemistry, remember that it's loss of oxygen. We have no oxygen over here. And it's also gain of hydrogen. You can see we have no hydrogens and we're gaining hydrogen. So this is definitely a reduction reaction. So reduction followed by deprotonation of the conjugate acid of the amine to make the amine. There you go. Pretty cool stuff. And again, when we get into chapter 22, we're going to see a whole holy host of reactions that you can do with amines. All kinds of cool stuff. So let's go down here and review what we've covered so far. We have covered iodination. Kinda, yeah, kinda no. That's in question 18.1. I want everybody to check that one out. We've covered bromination. We've covered chlorination. We've covered nitration, reduction, and we've covered sulfonation and desulfonation. So we've covered all those. And what I want to do now is take a break before we get into these two reactions here. And the way you would describe those two reactions to make 5 and 6, you can see that they're both have similar names. One is a Friedel-Crafts alkylation. That's where we're installing an alkyl group. And the other one is Friedel-Crafts acylation, which is where we're installing an acyl group. So alkylation and acylation. And since they're both Friedel-Crafts reactions, you can imagine if they're both named after the same people, they're probably pretty similar. And they are. But there are a few nuances to Friedel-Crafts reactions, and that's why I think it's a good place to take a little break.